Today we're going to be talking about the structure of the atom and what those numbers on the periodic table mean. So oftentimes when we think of an atom, it looks something like this. This is really set up to reflect the Bohr model of the atom, with our neutrons and protons in the nucleus and our electrons going around it in orbits. Now we know that this isn't the most accurate way to depict an atom, but if you're going to have to draw one, it's probably the easiest and closest way to do it. But let's talk a little bit more about that later. So the structure of the atom. First, let's get a definition of an atom. An atom is the smallest particle of an element that still retains the properties of that element. And all matter is made of atoms. If you have a chunk of gold, even if you just have one atom of gold, it still has all the properties of gold, even if we work it down to the smallest possible particle. But we can get smaller than an atom. We just don't have the properties of our substances anymore. We call these things subatomic particles. Sub meaning of or inside, atomic meaning the atom. So our first subatomic particle we're going to discuss is the proton. Protons are a positively charged particle and they occupy the nucleus. Generally we say they have a mass of 1 AMU or atomic mass unit. The atomic mass unit is essentially a unit of mass designed to measure, atoms. The symbol for a proton usually looks like a P with a superscript of a plus to the right. Or it can also be a P with a 1 and a 1 to the left. We call this isotopic notation. In this case, the 1 on top, the number on top, represents the mass of the particle. And the number on the bottom represents the charge of the particle, which in the case of a proton is +1. Now we also have neutrons. Neutrons are neutral. Now remember, protons are positive particles. Neutrons are neutral, not negative. They're neutral particles occupying the nucleus. They also have a mass of 1 AMU. But keep in mind, because they are neutral, they have 0 charge. Nothing, nada, niet, bupkis, nothing at all. So when we write the symbol for a neutron, usually it's a lowercase n with a 0 as a superscript up and to the right. Or it can be an lowercase n with a 1 over a 0. Once again, that 1 represents the mass and the 0 represents the charge. So those are the two subatomic particles that occupy the nucleus of an atom. And we'll get into how different numbers of those protons and neutrons work in just a little bit. But we do have a third subatomic particle, and that is what? You got it. That one is the electron. So electrons are a negatively charged particle, and they occupy space outside of the nucleus with a charge equal to but opposite of a proton. And this means that an electron is just as negative as a proton is positive. Now their mass, on the other hand, is exceedingly small. It is 1/1836th of an AMU. That is really tiny. I mean, let's think about this. It takes 1,836 electrons to equal the mass of 1 proton. That's really small. And so effectively, in terms of the level of chemistry that we're working with, we can essentially consider the electron to have virtually no mass. I'm not telling you they have no mass. I'm telling you they have virtually no mass. They are just that tiny. So when we write the symbol for an electron, it will be a lowercase e with a negative sign as a superscript up and to the right. Or it can sometimes be written as a lowercase e with a 0 over a 1 to the left. That 0 would represent that effective mass of virtually 0, and the -1 would equal the -1 charge of an electron. That perfectly balances out the +1 charge of a proton. So let's take a moment and let's fill in into our notes the symbol, the charge, the relative mass, and the locations of each of these subatomic particles. I'll give you a moment to do that. Great. So the basic symbol for the electron looks like this, the proton and the neutron. The charge of an electron is -1, the charge of a proton is +1, and the charge of a neutron is 0. The electron has essentially, now this is rounded, 1/1840th of a AMU. The proton is 1 AMU and the neutron is also 1 AMU. So the mass of a proton and a neutron are the same. This is something that's going to be really important to us as we go through literally everything else in chemistry. Now the relative locations. You probably remembered where the proton and the neutron are, but what about the electron? So the electrons are out in orbitals, not in orbits. That's the old Bohr model, where they traveled in planar orbits. We are now in these three-dimensional orbitals. Protons are in the nucleus, and so are your neutrons. So those are your three basic subatomic particles, their symbols, their charges, their relative masses, and their locations. All of these facts will actually take you really far in chemistry if you just remember them, because they govern the way that a lot of matter behaves based on the numbers of electrons, protons, and neutrons in the atoms themselves. So, it's time for a little joke. Let's see. It is full-on dad joke time. Are we ready? Okay. So, two atoms are walking down the street, and one atom says to the other, "Hey, I think I lost an electron." And the other one says, "Are you sure?" "Yeah, I'm positive." Yeah, I know. Let's try this one. A neutron walks into a restaurant and orders a couple of drinks. And as she's about to leave, she asks the waiter how much she owes. And the waiter replies, "For you, no charge." Yeah. You don't have to say anything. Let's get into the numbers in the atom. You should have your periodic table in front of you. Remember, if you are in New York taking Regents Chemistry, that is page 9 of your reference table. So, atomic number. Atomic number is the total number of protons in an atom. Now, for every single element, it has a unique atomic number. You can kind of think of the atomic number for each element kind of like its ID number. It doesn't change. It will always be the same for each individual element. Each element's atomic number is unique. Now, let's extrapolate that. If each atomic number is unique to each element, and it is the number of protons in an atom, what also has to be unique about each element? Well, that would be the number of protons in an atom. Every element has a different number of protons, and that's going to be really important to us because it's going to kind of govern the way that they behave. When we're looking at atomic number, it's usually in the upper left-hand corner on the periodic table. At the very least, it's going to be the largest number within the box for that element. It is oftentimes also in bold. There's also another number that we're going to be talking about, sometimes called atomic weight. We're going to be referring to it as atomic mass. So here in our example, I'm using krypton, and krypton has an atomic number of 36. It is the only element with the atomic number 36. Because its atomic number is 36, that tells us that krypton has 36 protons in its nucleus. Here in this example of a periodic table, our atomic numbers are above the symbols for each element. For example, here with carbon, we have an atomic number of 6. What's the atomic number for fluorine, whose symbol is F? What's the atomic number for lithium, whose symbol is Li? What's the atomic number for oxygen? What's the atomic number for aluminum? Great, we're getting the idea. This would also be the number of protons in those atoms. So I could also ask you, how many protons are in nitrogen, whose symbol is N? That would be 7. How many protons are in sulfur, whose symbol is S? That would be 16. Now, atomic mass. First off, we have the mass number and atomic mass, and they're not the same, and I just want to get this out of the way. Your mass number is the total number of neutrons and protons in an atom. So if we count up the neutrons and we count up the protons and we add them together, we will get the mass number. The mass number is always a whole number. This number at the bottom here is not our mass number. That's the atomic mass. The mass number is the number of protons plus the number of neutrons in an atom. And it is usually this atomic mass number rounded to the nearest whole number. So for example, 83.8 would round to 84. 84 would be the mass number of krypton. The atomic mass of krypton would be 83.8. So that is mass number, which is the total number of neutrons and protons in an atom, versus atomic mass. We're going to talk more about atomic mass in just a moment. So, if we were to go for the mass number of some various elements, let's look at carbon. Carbon with its atomic number of 6 and its atomic mass of 12.01, what would its mass number be? Well, carbon's mass number would be 12, because if we round 12.01 to its nearest whole number value, that would be 12. Let's take a look at aluminum. Aluminum down here, its atomic number is 13. Its atomic mass is 26.98. What would its mass number be? Well, the mass number of aluminum would be 27, because if we round 26.98 to its nearest whole number value, that would be 27. Remember, mass number is the total number of neutrons and protons in an atom. So how can we find the number of neutrons? Well, we subtract the atomic number, which is the number of protons, from the mass number, which is the protons plus the neutrons. So for example, here with krypton, our atomic mass is 83.80. We round that to its nearest whole value to find the mass number, which would be 84. If I subtract my 36 protons that I get from the atomic number, that tells me that krypton has 48 neutrons. And this will work for any element that has a mass number. Let's try a few. Let's give, which one do we want to do? Let's do fluorine. Fluorine is over here, symbol F. It has an atomic number of 9. Its atomic mass is 19, so 0.00, so we don't have to round anything. Its mass number is also 19. So how many neutrons would fluorine have? Excellent. 19 minus 9 would give us 10. Fluorine would have 10 neutrons. What about helium? Atomic number 2. Good. So helium would have 4 atomic mass number, because 4.003 would round to 4. And we have 2 protons, and that would give us 2 neutrons. What about boron? Atomic number 5, symbol B. How many neutrons would it have? If you said 6, you're absolutely correct. Boron has an atomic mass of 10.81. That would round to 11 for our mass number. We would then subtract the 5 protons to get our 6 neutrons. Great. So let's talk a little bit about the symbols for elements. Generally, when we write the symbol for an element, we write it using something called isotopic notation. The symbol for the element is the letter-based symbol with the mass number and the atomic number. Sometimes that number on top could be the atomic mass. You might see it written either way. So remember, your atomic number is your protons, your mass number is your protons and your neutrons. So here we have fluorine. I want you to take a moment and tell me, how many protons does it have? How many neutrons does it have? How many electrons does it have? And what is its atomic number and its mass number? So fluorine has 9 protons, 10 neutrons, coming together to make that mass number. It has 9 electrons, has an atomic number of 9, and a mass number of 19. Let's try another one. This is bromine. Bromine is one of the only elements that is a non-metal and a liquid at standard room temperature. In fact, it's the only non-metal liquid at standard room temperature. So let's find the number of protons, the number of neutrons, the number of electrons, the atomic number, and the mass number for bromine. Bromine would have 35 protons, 45 neutrons, 35 electrons. Now you might be wondering, how can we get the number of electrons? Electrons will always equal the number of protons because protons are just as positive as electrons are negative. And because of this, they balance each other out in a neutral atom. So if you know your number of protons in an atom, you also automatically know your number of electrons in an atom. Our atomic number would be 35, and our mass number here would be 80. Let's take a look at another one, and on this one, it's going to be a little more complicated. So this is sodium. Sodium is a very soft, reactive group 1 metal, and sodium also has a specific number of protons, neutrons, and electrons. Now, I'm not going to make you go hunting for it yet. So, what are the numbers associated with the sodium atom? So sodium would have 11 protons, 12 neutrons, because 11 plus 12 is 23, and that would equal our mass number. Our electrons would be 11. Once again, electrons will be the same as protons in an electrically neutral atom. Our atomic number will be 11, and our mass number is 23. I think you're ready to step it up a notch. Let's try to find the information for a mystery element. If an element has an atomic number of 23 and a mass number of 51, what is the number of protons, number of neutrons, number of electrons, and the complete symbol for that element? The number of protons in our mystery element would be equal to the atomic number. That would be 23. Our number of neutrons would be 23 subtracted from 51, so that's going to give us 28 neutrons. Notice, our number of protons and neutrons are not always the same, nor are they always very close together. That's something we're going to talk about more as we get in depth in the atom. The number of electrons should equal protons, so that would be 23. And our complete symbol for this element would be 51 over 23 with a V. Because if we look up atomic number 23, that gives us the element that symbol is V, and that is vanadium. Vanadium is commonly used as a coating on tools in order to make the metal harder and to make them last longer without damage. Let's try one more mystery element. So if an element has 60 protons and 84 neutrons, what's the atomic number, the mass number, the number of electrons, and the complete symbol for our mystery element? So we have an element with 60 protons and 84 neutrons, and that gives us all the information we need to be able to find our other four numbers and create our symbol. Our atomic number should be 60 because it's equal to our protons. Our mass number should be 144 because our mass number is always equal to our protons plus our neutrons. I just want to point out here again, our number of protons is 60, and here we have 84 neutrons. That's quite a difference. This does happen. Our number of electrons should be 60 because it will always be equal to our number of protons. And our complete symbol for this element would be 144, or our mass number, over 60, and the symbol's indicator is ND, uppercase N, lowercase d, and this is neodymium. Neodymium is commonly used in very strong industrial magnets. In fact, I can tell you kind of a gory story about neodymium. Neodymium magnets at one point were used in a common building toy called magnetics. And it had these little magnets that allowed all the parts to stick together, but they were really strong. But they were also very, very tiny, and it was quite easy for them to come out of the larger parts that they were embedded in. And children were swallowing these tiny magnets because little kids, I mean, let's be real, they swallow anything. Like they'll swallow pennies, Legos, you know, it's crazy, but they were swallowing these tiny little magnets, and then those magnets would find each other, and you know, opposites attract in the digestive system, and they were causing pinches and loops in the children's digestive systems. Ugh, it was awful. It was a huge story in the news when it happened, but that toy was taken off the market and then modified to remove those super strong magnets. Let's try one last practice in our lesson today. You can draw this table in the bottom of your notes or on a scrap piece of paper. I've given you the periodic table information for 3 elements, calcium, argon, and bromine. I would like for you to tell us the atomic number, the mass number, the number of protons, the number of neutrons, and the number of electrons for each of these 3 elements. Let's see how you did. Calcium's atomic number is 20. Its mass number is 40. Its number of protons is 20. Its neutrons are 20. And its number of electrons are also 20. Argon. Argon's atomic number is 18. Its mass number is also 40. If you look at calcium, its average atomic mass, or atomic mass, is 40.08, and argon's is 39.948. Both of those round to 40. I want you to notice that even though both of these mass numbers are 40, they're for different elements. This is one of the reasons why mass number is not a good indicator of element identity. The one number that will always get you to the identity of an element is its atomic number, which is equal to its number of protons. The number of protons in argon is 18. Its number of neutrons should be 22, and its electrons will also be 18 because it's the same as the number of protons. Lastly, let's take another look at bromine. Bromine's atomic number is 35. Its mass number is 80. Its proton number is 35. Its neutrons are 45, and its number of electrons are 35. I want to thank you for joining us in our lesson today. I hope you learned a little bit about the structure of the atom and atomic number, mass number, and how to calculate the number of protons, neutrons, and electrons for any element on the periodic table. In our next lesson, we're going to be talking about average atomic mass, what atomic mass is, what isotopes are, and how we can calculate out the average isotopic mass for virtually any element. Thanks.